Welcome to lesson 1.3. The title is A First Look at Limits. The objectives are to explore long-run values and to begin to understand the concept of limits. We're going to talk about the definition of the shifted geometric sequences, and we're going to use algebra to find the long-run values. Please use the investigation that we did in class today to follow along with this lesson. By definition, a geometric sequence is when you multiply by what we call a common ratio. So for example, you're still going to need the starting value, and it's usually represented by either u sub 1 or u sub 0. And then our routine itself is going to be un equals to the common ratio times un minus 1, which is the previous number. The difference between geometric sequence and a shifted geometric sequence is that a shifted geometric sequence includes an added term in the recursive rules or routine itself. Again, you're still going to need a starting value, which is usually represented by u sub 1 or u sub 0. And you're going to have un is equal to some type of common ratio times the previous term plus a constant term. What we did today during class are all shifted geometric sequences. And let me explain a little bit further on why that is. You notice that in each part of the investigation, it approaches what we call a long-run value. And that long-run value is that it levels out no matter if you added or subtracted a term. So if you recall part 1 and 2 of the investigation, the long-run value after taking away the Skittles and adding in Skittles, it comes out to be about 48. Once we get to 48, the number of Skittles taken away and the number of Skittles given are the same, so therefore that value of 48 will never stop changing. Part 3 and 4 of the investigation, when you put that into your calculator, when you put it in the sequence mode of your calculator and you scroll down, when you scroll down far enough into the table, you're going to see that it stops changing at 12.5. For part 5 and 6 of the investigation, again, it did the same thing. When you scroll down far enough, you will see that it stops changing at 60. Those are what we call the long-run value. It's the LRV. Let me look at how I could possibly find the long-run values using algebra instead of relying on my calculator. Let me take a look closely at the part 1 and part 2 of the investigation. Part 1 of the investigation says that you start out with 10 Skittles. So you notice that I have u sub 0 is equal to 10. The recursive rule is un is equal to un minus 1 times, I took 1 minus 0.2 because the taker takes away 20%. So that's 1 minus the 0.2. And the giver gives back 10. So that's why I added 10. On part 2, you also notice that they begin with 25 Skittles. The taker also takes away 20%. So my common ratio is 1 minus 0.2. And the giver also gives 10. Both part 1 and part 2, the long-run value that you found using the table is 48. Technically, it should be 50, and the reason is because we had to do some rounding because we couldn't take away part of the Skittles. When you have 0.5 of a Skittles, we had to round it up to 1 full Skittles. So the rounding does affect the long-run value just a little bit. The long-run value for this, if you put into your calculator, you're going to find that it equals to 50. All right, let me show you how to do this algebraically. For part 1 and part 2, the information is very much the same. The only thing that's different is the starting value. When you're looking for the long run value, it really does not matter what your starting number is. All right, so let me cross that out, because even if you start with 10, 25, 35, 100, whatever it might be, it will still end up at 50. All right. What gives it the 50, what gives it the long run value of 50 is the recursive rule itself. Okay. So here's what I do to find the long run value. I'm going to pretend that the UN, which is the very last number on the table, it already approaches my long run value. So I'm going to pretend that UN is the long run value. Okay, again, I don't know what it is, but I will find it. All right. Now, if my last value is already at the long run value, then that means that the number before that will also be at the long run value, because it already approaches, it's already at that long run value. So it's not going to change. So whether is, pretend that it is the 99th term versus the 98th term, it'll still be the same number. Okay, so let's pretend that it is LRV. Let's pretend that it is the long run value. Now, let me simplify this one a little bit. 1 minus 0.2 is the same thing as 0.8. And then I have a plus 10 at the end there. Okay, you notice that if I rewrite part 2 into using the variable LRV, I'm still going to get the same exact equation. All right. Now, I notice there are LRV on both the left-hand side of the equal sign and the right-hand side of the equal sign. So what I'm going to do is I'm going to combine like term. So I'm going to subtract 0.8 LRV from both sides. So LRV times 0.8 is the same thing as 0.8 LRV. So I'm going to get rid of it. I'm going to subtract 0.8 LRV from both sides. All right, let me bring down my equal sign here. All right, so this LRV that you see, the first LRV, is the same thing as 1 LRV. So 1 LRV minus 0.8 LRV is going to equal to 0.2 LRV. Okay, so again, 1 minus 0.8 is 0.2. And then on the right-hand side of the equal sign, the LRV times 0.8 minus 0.8 LRV will undo each other, and it will become 0. So what I have is just 10. All right. So this 0.2 LRV is the same thing as 0.2 times LRV. So I'm going to undo that multiplication by dividing it out. I'm going to divide both sides by 0.2. And when I divide both sides by 0.2, I'm going to get the LRV, which is the long run value, which is what I'm looking for, is going to equal to 50. And we already knew that by just if we enter this into our calculator. If we scroll down far enough, you're going to find that it equals to 50. So pause for a second and look at what we did again and see if you can verify all the the long run value for part 3 and part 4 of the investigation. So keeping in mind that part 3 and part 4, it has a different starting value, but the taker takes away the same percentage, which is 40%, and the giver gives 5 back. When you type that into your calculator, you know that the long run value is 12.5. So to find the long run value using algebra, the first thing we're going to do is we're going to completely ignore what the starting value is, because it honestly doesn't matter what the starting value is. I'm going to replace the UN with the long run value. I'm going to pretend that we already know what it is. All right. Now that also means that the previous term, the term before the long run value, will still be the same thing, which is the LRV. I want to simplify the 1 minus 0.4. Well, 1 minus 0.4 is 0.6. And then I have the plus 5. So next thing I'm going to do is I'm going to combine like terms. So LRV times 0.6 is the same thing as 0.6 LRV, which I'm going to subtract it out from both sides of the equation. All right. So keeping this in mind, LRV is the same thing as 1 LRV, and 1 LRV minus 0.6 LRV is going to be 0.4 times LRV. Remember, LRV is our long run value, which is what we're looking for. On the right-hand side of the equal sign, this will undo each other, so it becomes 0. What I have is a positive 5. So then if I divide both sides by 0.4, I'm going to get the long run value, which is what I'm looking for. The long run value will then equals to 12.5. And again, this is just a verification because I already knew that number from looking at the table. Now, what I'd like you to do is try it for part 5 and see if you get 60. So let me wrap up lesson 1.3. We've looked at 3 different recursive routines so far. Anytime you have an arithmetic sequence, it is going to be linear, and it's either decreasing or increasing. So if it's increasing, it's going to look like this. If it's decreasing, it's going to look like this. And it's going to be either increasing by the same amount or decreasing by the same amount. That same amount is called the common difference. All right. The second sequence that we have looked at is what we call a geometric sequence, and it is a curved graph. It is non-linear. If it's decreasing, it usually does level off at 0. For example, it looks like this first graph here. If it's increasing, it usually does not have a limit, and it will continue to increase. Anytime you have a common ratio of a value that's bigger than 1, it's going to be increasing, and it has no limit. It will keep going up and up and up. All right. What we looked at today is what we call a shifted geometric sequence. Again, it is going to be curved. It is nonlinear. If it's decreasing, it will level off at a non-zero. So, for example, if you look at this first graph here, if it's decreasing, it will go down, but then it will level off and it won't be at a 0. It's what we call the long run value. In calculus, it is called the limit. Now, if it's increasing, then it will level off as well. And again, it will level off at a value that we call the long run value.